Quantum cryptography is a revolutionary field that uses the laws of quantum mechanics to create unbreakable encryption. In this presentation, we will explore the basics of traditional cryptography, the principles of quantum cryptography, and the latest research in this exciting field. Quantum cryptography is an emerging technology that holds great promise for secure communications. Unlike classical cryptography, which relies on the complexity of mathematical algorithms, quantum cryptography uses the laws of physics to provide unbreakable security. The key feature of quantum cryptography is quantum key distribution, which alerts users to eavesdroppers by the nature of the quantum states. This makes it a robust defense against the threats posed by quantum computing. While still in development, quantum cryptography has the potential to revolutionize the field of cybersecurity and provide unparalleled security in the face of evolving threats. Quantum cryptography uses quantum mechanics to offer theoretically unbreakable security. Unlike classical computers, which operate on bits that are either 0 or 1, quantum computers are based on quantum bits or qubits, which can be both 0 and 1 simultaneously, a state of ambiguity called superposition. Classical cryptography depends on complex math. Quantum cryptography, also known as quantum encryption, refers to various quantum methods for encrypting and transferring secure data based on the naturally occurring and immutable laws of quantum mechanics. It provides security services such as encryption and authentication. Quantum key distribution alerts users to eavesdroppers by the nature of quantum states. QKD is a robust defense against the threats posed by quantum computing. Quantum cryptography's potential for secure communications is unparalleled. It marks a significant shift in cybersecurity. A bit about quantum bits and qubits. Quantum bits, qubits, or groups thereof, are characterized with numbers called amplitudes, which are akin to probabilities but aren't exactly probabilities. In a quantum computer, registers consist of one or more qubits in a state of superposition characterized by a set of complex numbers. A single qubit is characterized by two amplitudes. Different qubits can behave to an observer but have different amplitudes. There's an example of the shadow of an object. A single qubit is characterized by two amplitudes. The upshot is that the different qubits can behave similarly to an observer with the same probability of seeing 0 for both qubits, but have different amplitudes. This tells us that the actual probabilities of seeing a 0 or a 1 only partially characterize a qubit. Just as when you observe the shadow of an object on a wall, the shape of the shadow will give you an idea of the object's width and height, but not of its depth. In the case of qubits, this hidden dimension is the value of its amplitude. Is it positive or negative? Is it a real number or an imaginary number? A quantum computer transforms a group of qubits reversible by applying a series of quantum gates, and then measures the value of one or more qubits. From a mathematical standpoint, qubit algorithms are essentially a circuit of quantum gates that transforms a set of complex numbers, the amplitudes, before a final measurement where the value of one or more qubits is observed. Quantum gates. The concept of amplitude and quantum gates are unique to quantum computing, whereas a classical computer uses registers, memory, and a microprocessor to perform a series of instructions on data. A quantum computer transforms a group of qubits reversible by applying a series of quantum gates and then measuring the value of one or more qubits. Quantum computers promise more computing power because with only n bits they can process 2 to n number the qubits amplitudes. Hadamar's quantum gate. The Hadamard quantum gate, usually denoted H, the Hadamard gate is defined as follows. Quantum mechanics tells us that the qubit will behave deterministically. That is, if you observe this qubit, you will always see 0 and never 1. In other words, we've lost the randomness of the initial qubit. What happens if we apply the Hadamard gate again 2 qubit. This brings us back to H in a randomized state. Indeed, the Hadamard's gate is often used in quantum algorithms to go from a deterministic state to a uniformly random one. Shor's algorithm is a quantum algorithm that causes an exponential speed up when solving and factoring discrete logarithms, and elliptical curve discrete logarithms problems. You can't solve these problems with a classical computer, but you could with a quantum computer. That means that you could use a quantum computer to solve any cryptographic algorithm that relies on those problems, including RSA, Diffie-Hellman, elliptical curve cryptography, and all currently deployed public key cryptography mechanisms. In other words, you could reduce the security of RSA or elliptical curve cryptography to that of Caesar's cipher. Grover's algorithm. This form of quantum speedup is the ability to search among n items in time proportional to the square root of n, whereas any classical algorithm would take time proportional to n. Quantum computer challenges. Why is it so hard to build a quantum computer? Because you need extremely small things to play the role of qubits, about the size of electrons or photons, and because qubits must be so small, they're also extremely fragile. Qubits must also be kept at an extremely low temperature, close to absolute zero, in order to remain stable. But even at such freezing temperatures, the state of the qubit decays and eventually becomes useless. We don't yet know how to make qubits that will last for more than a few seconds. Another challenge is that qubits can be affected by the environment, such as heat and magnetic fields, which can create noise in the system and hence computational errors. In theory, it's possible to deal with these errors as long as the error rate isn't too high, but it's hard to do so. Correcting qubit errors requires specific techniques called quantum error correcting codes, which in turn require additional qubits and a low enough rate of error, but we don't know how to build systems with such a low error rate. Quantum key distribution is a secure method of key distribution by generating unbreakable encryption keys using a principle of quantum mechanics. It is based on the principle that any attempt to measure a quantum system will disturb the system, making it impossible to clone or copy the key without detection. QKD works by encoding the information into quantum states, which are then transmitted to the receiver. Any attempt to intercept the transmission will be detected, ensuring the security of the encryption key. Quantum entanglement is a phenomenon where two particles are connected in such a way that the state of one particle is dependent on the state of other particles. Entangled particles can be used to detect eavesdropping and quantum key distribution. Any attempt to measure the state of one of the entangled particles will disturb the state of the other, alerting the receiver to the presence of an eavesdropper. Quantum cryptography protocols are used to create secure communication systems. BB84 protocol is a widely used quantum key distribution protocol that uses polarization of protons to distribute a shared key between two parties. E91 protocol is another quantum key distribution protocol that uses entanglement to distribute a shared secret key between two parties. Is considered to be more secure than BB84 protocol. Quantum hacking is a cybersecurity threat that exploits vulnerabilities in quantum systems. The goal of quantum hacking is to gain unauthorized access to sensitive quantum cryptography attacks. The intercept resend attack is a type of attack on the transmission of an encryption key where a third party intercepts and then resends the key to the intended recipient. This can compromise the security of the communications channel and put sensitive information at risk. A man-in-the-middle attack is a type of quantum hacking where an attacker intercepts a message and alters it before sending it to the receiver. We can defend against these types of attacks using authentication protocols and quantum key distribution protocols. Challenges in implementing QKD. It can be challenging due to the need for specialized hardware and the limitations of the communications channel. However, ongoing research and development are addressing these challenges. This is a demonstration video of quantum key distribution, as I did not have the access to a quantum computer or software. As we can see from this video demonstration, whenever the properties of a transmission is altered, it is seen by both receiver and sender. The advantages and disadvantages of quantum cryptology versus similar protocols. One of the main advantages of quantum cryptography is its ability to detect eavesdroppings. The limitations are these, is that the communication range of quantum cryptography is currently limited to around 10 miles, while classical cryptography can be used to communicate over much longer distances. In conclusion, quantum cryptography is a promising technology that can revolutionize the way we communicate securely, leveraging the principles of quantum mechanics to create unbreakable encryption that is secure against even the most sophisticated attacks. One day they'll have the potential to break RSA, Diffie-Hellman elliptical curve cryptology, that is, all the public key crypto developed or standardized. However, currently quantum computers are very difficult to build or scale. Thanks for your time watching this presentation.